Hello world and welcome back to my channel. We'll continue to do some Vulkan programming, and I will be honest up front. Vulkan can be tough. There's a lot of complexity under the hood, and understanding how all these pieces fit together is challenging, but also really rewarding. So in today's episode we'll cover a lot. We will start by making a few corrections from the previous episode. I like to do this in every video, so we are always building on the right foundation. Then we continue by creating Vulkan instance, then we will set up Vulkan surface and look at how to find devices which support all the requirements our application needs. We'll also dive into the extensions, both instance and device, as well as Vulkan device features. And of course, there will be plenty of C++ and some CMake along the way. This is going to be a long video. I recommend grabbing yourself a cup of coffee, like I did. I like coffee, and if you think I'm doing something useful, you can buy me a coffee following the link in the description. Okay, so I'm wearing my Vulkan hat. I hope you enjoy this. Let's start. So as I mentioned, we begin today's video with some corrections to the previous video. There are not a lot of corrections, but I just found that, for example, with this macro we used, this thing is not really necessary. It's not a big thing that it exists, but I just prefer to always remove everything we do not need at the moment, and in case we need, we will re-add this. But for now, just as a reminder, this thing, it just tries to create a unique name for this variable, for the temporary. The idea is if you have multiple usages of this macro, and of course there are multiple variables with the same name, there will be warnings, and as you remember in our project, the warnings are errors, so it will not compile. So that's why I just introduced this temporary name variable thing. But we can make it simpler if you just wrap these lines in a code block. We don't need to concatenate everything. It will be a little bit simpler. So let's just start by fixing this. And the second correction is how we are using and introducing the third-party dependencies. I briefly mentioned that every time we try to reconfigure, for example like this, it will think that we will download something. Indeed, it prints something, and my assumption was that if there is some kind of internet problems, it will not compile, although the code is here. That's not true, because I tried to disable my Wi-Fi, so without internet it still works. So somehow fetch content that checks for this directory. But anyway, I just like the things to be pretty, and I will add the check for existence of this folder. So if we downloaded once the dependency, CMake will check if it exists or not, and if it exists it will just add subdirectory. It's not the first time it will try to get this dependency. And also I will change the name of the source folder to the name of the version. It's absolutely not necessary, the cosmetic thing, but it will help just opening the folder, immediately see the version. And if, for example, we want to update it, of course we need to reopen the CMake, changing the tag. So let's do this. Okay, so it works. So as you can see, as soon as I changed this thing and ran CMake reconfigure the project, so it appeared, we can safely remove the old directory. Here it complains that our top level CMake doesn't have this project command, so let's just add it here. And we call it Tpod with C++. The thing is, we already have the project defined here with this name. I don't know what happens if we have two projects with the same name. Let's try to save and see. Apparently nothing bad happened, so it works. But let's remove the project from the application, from the executable, and we will have just in one place. So it works currently, so we have it here. As you can see, it doesn't print downloading this format library. Once again, if we decide, for example, to change the version, we can remove this one and we can reconfigure the project and check it's appeared, and here it should say that it's downloading this. Good, so this works for format library. Now let's do the same for our window library. As you can see in the output and here in the directory structure, we have the new name for the folder. We can remove the previous one. And I just noticed that when it builds and downloads the window library glfv, it builds some documentation which we actually don't need. And if we open the main CMake file for the library, we see a bunch of options here. So this is off, and here it says to build the docs and to install, which again we don't need. We will not install, we will use the project by ourselves and use it out of the build directory. We don't need builds, we don't need tests, and we don't need examples. So let's just set this thing to off to reduce the amount of work we need to do. And that's how we do it. So basically we define the variable with the same name as option here, and we tell CMake to cache it, basically to save it. So when you use the cache, CMake builds a special file called CMake hash, where it keeps these cached variables and options. So options by default are cached, and we can force the option also to be cached. So the next time you run the CMake, it will remember what was set off. Sometimes it's super confusing, because if you will try to set this variable here, for example, it will not work because it's cached, and it will take the value from this file. So in this case, if you want to change it, we need to remove the file or just remove the build directory. And since we're caching this and want to turn it off, we need to do it the first thing before this glf file CMake is run. Yeah, so now I think if we remove again this folder and reconfigure the project, we will not see this building documentation thing. So let's check. yeah, there was error, and I just removed the build directory, so probably again something was cached here. That's the thing with CMake. If something's wrong, the first thing you need to do is to clear the build directory. That's why it's recommended to build in so-called off-source building. Then you put everything CMake related in a special folder, and you can just delete it and be happy. Anyway, let's look here. Format library, it's okay, and I'm looking for a window library, and I do not see, yeah, here. So downloading this, and I do not see anything documentation related, so apparently this works. So now let's try to rerun CMake again and to see it works. Now it uses this already existing folders. That's good. And the next thing to do, let's create a new branch for today's video. And yeah, so the idea is to have one branch per video, so if somebody follows from, let's say, second video, he can just take the branch and see what's happening instead of just taking the latest version. Finally, we are ready to start talking about Vulkan. And the main question, how do we even start? And that's actually a very difficult question. I can't imagine, for example, for the newcomers who just start to learn a graphical API or Vulkan in particular. Oh, it's super difficult, I think. I have opened the Vulkan specification. So this is basically the Bible of Vulkan. The specification defines all the rules for the API, and it's huge. If you just start to scroll it with mouse, I think I need a couple of days to reach the end of this file. There are other formats of this file, so there is a chunked version of the specification, there is of course a PDF version, but I prefer to use this, everything on one page. It's very slow sometimes, it takes a lot of time to open, but I just use Ctrl F to search something. And for example, talking about the complexity, let's pretend we have a shader code, and the ultimate goal of our application is to run a shader. As you know, shader is a small program similar to normal CPU, for example, C++ programs, which runs on GPU. And yeah, that's the thing. So we need just to have this small amount of code to run on another device. Again, if you compare it with C++, you just try it, compile it with CMake, or just directly calling compiler, for example, GCC, and it's done. When you can run. But with Vulkan, it's difficult. For example, let's look at it's called create shader model. Let's not go very deep, just some basic information for now. Let's look at this function from the end. So almost every Vulkan function follows the same pattern. Oh man, this specification is really slow, so I can't even select with mouse without legs. Anyway, so this parameter, usually it's the last parameter, is the result of this function. So the function by itself returns the error code or not error, a success code. So if you can see the return codes, it's success. Everything is okay, and we always should aim this result for every Vulkan function, and these are the possible errors. But if everything is okay, the shader model which this function creates just goes into this variable. This allocator, we will not use it. It basically tells if you want to allocate somewhere in our memory, we need to use this variable. It's probably for embedded systems or systems with small amount of memory and which we want to control. But in our application, we will not use it. And this shader module create info is basically information about what we are going to create. So there are different kind of create infos which we will see throughout our applications. The shader module create info has the code itself, size, different flags. Almost every structure will have these two fields, type and next. We'll see what exactly this means later. So these things are, no, we can use it, but this thing we don't know. What is it? It's written here, it's a logical device. It's basically the software representation of our hardware. So if you have a device or multiple devices, in Vulkan they're called physical devices. So we need first to select a physical device, and then from this physical device we create a logical device. So we set the options we want to use with this device. So for example, turn some features on or off. Imagine we can use multiple different devices with different features enabled. I don't know why you want to do this, but it's possible. So the physical device, it's just one thing which exactly represents the piece of metal in your computer, and the logical device is some abstraction over it. And you create the device with surprise create device function. Let's just jump into this. As you can see, it's very similar to what we saw before. So the last parameter is the result of this function, allocator, some device create info, with different kinds of information we want to provide with this device, exactly what I mentioned. For example, which features we want to use, extensions to enable for this device, all this kind of stuff. We will see this later when we'll actually create it. And again, there is a new parameter which is necessary to create the logical device. It's a physical device. And here the documentation tells us we don't create this time, but we select from the existing. Sounds very logical, right? So we have device, we need to select it. Again, you can have multiple devices on your machine, so you need to enumerate, select all of them. And this thing is new to us, so we don't know yet. It's instance. If you jump to this, we can see again the result, allocator, and create info. And finally, there is no dependencies to this function. And this basically the ultimate starting point for all Vulkan applications. And we will also start with this thing, with instance. And let's look what specification tells us about instance. I did this very long time ago, so I don't remember exactly, but I just know that OpenGL is famous for its global state. And here the first line is saying us that the Vulkan has no global state, and the state is stored in the instance object. So yeah, you can have multiple Vulkan applications running on the same machine without interfering each other. That's a good thing. So it's basically a state for our application. Here it says that create an instance initialized the Vulkan library. And the interesting thing, looking a bit ahead, so we need some special things like extensions. That's a very confusing part. There are multiple kinds of extensions, device extensions and instance extensions, and we will use some of them. And before creating an instance, we need to check if the current version of the instance supports this. And usually if you have the latest driver, that means that your instance version will support the new extensions. So yeah, the recommendation is always to have up-to-date driver, and especially if you develop the Vulkan application, you have to do this. And another interesting thing to check if your instance version supports everything needed, you need to call this enumerate instance version. And it says that's provided in Vulkan 1.1. That means that if you have, for example, a very old GPU which doesn't support Vulkan more than 1.0, you will not able to call this function. So we need a special check that our version is whatever we will use. And by the way, the minimum requirement for our teapot application is Vulkan 1.3. It's still possible to use earlier version, but 1.3 introduces some very nice features which we will use. For example, the mesh shaders by themselves, they are not supported earlier. And the descriptor indexing thing, we will see it later. Yeah, the first step before creating the instance is to check the version of the instance on the machine which runs this Vulkan application. And the second thing is to check the supported extensions. And only after these two steps, if they are successful, we can be sure that we can create an instance we need and use it throughout our application. Yeah, it was a lot of code. Now let me explain what I did. By the way, I installed the new extension for Visual Studio Code. It's called Highlight Line. So now if I select a line, it will be highlighted. So let's see what's happening here. I added the new class to our graphics library, and this is Graphic Manager. So basically this will be our storage for everything. As you remember, we need to initialize a lot of different objects, Vulkan objects, instance, device, pipelines, shaders, and so on. And this is the place where we will store it. And this is the place which will be responsible for creating all this stuff. Let's look at CMake, how it's done. So this library, it's static. So the name of the library have the same properties as before. Since we will use this library for linkage to other libraries, I made this public. I'm actually not sure if I need to make this target sources, because the code will work without this, but I remember I read that some editors not require, but they look into this sources to display the source code in the editor tree. For example, this was the case for Visual Studio, not the code, just the big Visual Studio. It was ages ago, so I don't know how the things are now, because I'm not using Visual Studio. But anyway, so here I just maintain the list of necessary files. Everything is organized. So public or private, I don't know, honestly, if it's necessary. But anyway, of course, CPP is necessary, because without CPP, it will not compile, right? HPP is under the question, but I will keep it anyway. So this implementation file, so for example, here the function for instance version checking, this thing is used solely by the library, and it will not be exposed. That's why this functions will be set as private, so just to not to leak it to outside world, this include folder is necessary. For dependencies, for example, when we link graphics manager lib to, let's say, main application, then we need the definition of graphic manager, so we need the include directory. And as mentioned, this source directory is not needed for outside world, but it's needed for this library, so this line is necessary if you want to include, for example, this header. Also here, the dependencies we need, formatting, utilities from before, warnings, and of course we need Vulkan library. So CMake already have a predefined set of search paths, so it knows how to search different famous things. So Vulkan is one of these things which CMake aware of. So that's why when we call this find package, it tries to search somewhere. I don't know honestly how it's done. We can look into this, but it's not important. So the thing is, CMake searches this library. So if it's found, we continue. If it's not, there will be a configuration error. And of course, we link this library here. How do I know the name of the library? Well, it's written in CMake documentation. Let's see how it's done. Yeah, so here, find Vulkan was added in version 3.7, and we use much newer function. And here the list components, they actually were added in 3.24. The components are another thing. We will use, for example, we need this thing for shader compilation, and this is the imported target. So yeah, here documentation says us that's the name of the Vulkan library. Another important decision I made, I can of course put all these small pieces of code directly into the graphics manager, but for learning purposes, it's better just to show the small amount of code on the screen, and actually I prefer by myself this kind of style, so I just split the code into small chunks and prefer to use the small functions. It's just much easier to read than you have a small amount of code on one screen. Yeah, and the graphics manager by itself does not do too much yet, so it has default constructor which does nothing, and the user have to call this initialize function, and this in function will call different steps to initialize the manager. And the first step is to check instance version, as you can see. And here what I talked before, this function, if we search in documentation, let's use the small chunked version because it's just much faster. So it tells us that this requires the version of functionality, blah, blah, blah. And this is the important thing. It's available started from the version 1.1. That means that if you have version less than 1.1, I don't know what will happen. So some exception, segfault, I don't know. But there is a way to check this. There is another Vulkan function which called get instance pros address, and what it does, it just returns a function pointer for a command. So you have a name, you call this function, and it returns the pointer to this function. So here the documentation tells us it can be null if commands not depend on any instance, and indeed our command, this one, not depends on any instance, so you can see it only has output. Yeah, so that's the way to check. If the implementation can't find this function, that means that we are using the very, very old Vulkan version, and we can do nothing here, so we just skip. So the next thing is we check the actual API version, and as you can see, it can return something other than success, and we need to check this, and yeah, we will do this basically for almost every Vulkan call. This function returns the API version. It will be just some cryptic number which we can read by ourselves, just shifting some bits here and there, or just use this helper Vulkan functions to extract the major, minor, and the patch version. And in these lines, we check if the retrieved instance version actually is sufficient for us. And for this, I created another helper struct which lists the required API version, major and minor, so the patch is not that important for us. The reason I added a dedicated class for this is because we need these versions multiple times during initialization, and I just prefer to keep everything in one place. So if you want to change it later, it will be obviously just one place. So here again, if the version is not enough, we can't do anything, so we just report this to user and exit. And in the end, if everything is okay, we just print the version. So let's see if this works. So I already built, it builds successfully. So it starts our empty window. And I have another machine. I tried with Wayland Window Manager. And on Wayland, the window works differently. So the Wayland requires at least one present to the surface just to show the empty window. So if you're using Wayland and for some reason do not see the empty window, you have to wait until we reach the point where we clean and present on the screen. It will be not soon, but yeah, it will happen in the future. and it doesn't print anything simply because we didn't use manager at all. So let's fix it now. As you can see, I added the dependency here for our main application, and this is what I was talking about, the private and public visibility for CMake. So if we press the hint, Visual Studio shows us only what we made as public, so it doesn't show the implementation details here. It's just details, small details, but nice to have. Yeah, so as you saw, it compiles, and now if you run it, it prints the current version. So on my machine, that's the version I'm using, and it's indeed enough. It's indeed more than 1.3, which was set here. And just out of curiosity, if we try to do this, compile and run again, you can see it crashes with this information here, this fatal error and the result. So yeah, congratulations, this was the first touch of Vulkan, and that's only the beginning. Now let's look again what we need to create an instance. Of course, we need create info, and inside this info, what's important is these extensions. Layers, not so much. I will talk later about this. But extensions, yeah, that's another quite confusing part of Vulkan, because extensions can be either instance or device. So two kinds of extensions. And for example, when we create a device, we need one set of extensions. If we want to create an instance, we need another set of extensions. But what are extensions? As the name extension suggests, it's just a way to extend the API. For example, there is a core API and there is a specification with all the rules. But for example, some vendors want to add something new which doesn't exist in specification, and they can do it with extensions. The same thing happened with Mesh Shader. So before it became part of Vulkan, it was an extension from NVIDIA. And yeah, the way they introduced it was through extensions. So the programmer had to add this special, I don't remember the name of this extension, it was something like NVIDIA Mesh Shader extension. That's basically it. So you add the special structures, and then the driver probably knows how to work with it. I don't know actually. And I think it's not that important to know how things work. So the only main thing is to remember for now is that extensions can be two types. And how do we know which type? There is, of course, a specification for this, and each extension lists which kind of types it has. So for example, this acceleration structure is a device extension, and I don't know, some comparative matrix also device extension. For example, this display is an instance extension. That's the way we know if the extensions we have to add it to instance or to device. And the next question is, how do we know what we need? For example, shaders. Let's check Mesh Shader extension. Yeah, so this extension is a device extension, so we don't need to add this to instance. But I know that some windowing specifics, they require instance extensions. And the next step is to figure out how we find the extensions. Spoiler, we will use again GLFL library because it manages the window, so it knows. And first let's write some code, and then I'll explain a bit more about this. First of all, similar to the API version, I created a special struct to hold the extensions here. That's because we need this multiple times, and I prefer to keep it in one place. So for now, what we are doing, we just redirect the call to JLFI library, and it returns the extensions which are absolutely necessary for a window application here. So it just retrieves the names. As we go, we will add more extensions as we find we need them, but for now, let be only this. Let's just put a breakpoint here to see what exactly returns. And the magic itself happens in this check required instance extensions. So what it does first, it just prints what is required, and then that's the interesting pattern in Vulkan we will see in many places. The Vulkan uses one function to get the number of extensions, and these are extensions which are available for us for our instance, driver and the graphics card and all like this. The problem is, as you can see, so the last parameter should be our return type. Basically, we need to provide a piece of memory where these extensions will be written to, but since we don't know upfront how many extensions are for some GPU, it's not possible to know upfront. The API provides this call. So if you set the last parameter of this function as null, it will fill the extension count with the number of extensions. So that's why we call it twice. First we get the number, and then they allocate the necessary amount of memory, and the second call we get these extensions. Of course, we check that nothing fails, so I don't know why, but theoretically it's possible. It returns the extension properties. It's a struct with the char array and the version, and we just compare the required extension, which is a string, so we can compare it with the char, so it will be converted automatically by C++. And yeah, so basically we look at every required extension, then we see if presented in the list of available extensions. If not, that means sorry, we can't proceed, we can't do anything here, so we stop our application. And if it exists, we just continue with the next extension. So here I can't use continue keyword because it will continue this loop, but I want to continue the outer loop. That's why I use the label. I think that's the only way ever I used the label in C++. Maybe there is some other way, but that's quite simple and readable. So yeah, that's how it works. Again, just as a reminder, up to now we have checked the instance version. Is it sufficient for us or not? And then we need to know the extensions for our GPU. Currently it's only window extensions, but later we will add. As you saw, I added a breakpoint here. And let's see what this thing returns. So I hit F5, and what's going on here? Yeah, so I didn't put back the required API version. I'm still using 1.5, which doesn't exist at the moment of recording. Now I didn't compile it, so let's build. Now it should work. So it shows us that GLFA requires 2 instance extensions. It's a surface and XCB surface. That's operating system and window specific. We will come back to surfaces not very soon, but yeah, eventually, and we will look more. All you need to know for now is to create an instance, we need these two extensions. We can just comment everything out because for now, since we are not rendering and do not create any surfaces at all, we don't need this, but I just want to show why we need instance extensions, and we absolutely 100% will need it in the future. So yeah, let's start with the simple stuff. And it prints us this required things, which is good. And now with all this, we are ready to create an instance itself. Let's just do it. This function is pretty simple. So what it does here, we need to prepare a create info just to fill it with different things. Almost each struct in Vulkan require this S-type thing. That's how basically the Vulkan knows which struct is used, because it's always the first type in the struct. So if you open this, you see in almost every create info, the first field is S-type. Here we see as well type. And this is necessary, for example, when we create a chain of different informations. We will see, for example, this pnext, we can chain another info, and this info is typed as void, as you can see. And the way Vulkan knows which actually structure it deals with, it probably checks this type field. It's very tedious to write it by hand. Maybe we can use a helper. I didn't use it before, but maybe it's a good thing for me to try. So there's utility and some helpers, and one of them is struct helper. If you look inside, it just provides us this S-types for different kinds of structures. So let's just try to use it, and we'll see, will it work? I honestly don't know. Why does it say it's not defined? Because it's namespace. Like this. And we will do the same for this thing. If I just jump to it, it jumps directly to the definition. Yeah, so the create info requires a type, chaining not the case when we use it, flags a 0 for this thing. Let's keep for now application info. Layer count, that's another interesting thing. While extensions had some functionality by vendors, for example NVIDIA, AMD, layer in some sense also extend functionality, but it inserts a code between our application and, for example, the driver. And this is very important when we want to check for correctness for usage of the API. As you remember, I showed you some calls are huge. Let's actually open it again and let's just take a random command, vk draw, for example. This command, some parameters, and the valid usage. That's very important stuff. And if we can see here, it tells for valid usage what should be. So for example, if sampler was created with this parameters, then something to be like this. And as you can see, the amount of these rules is just tremendously huge. And I don't know, for a normal human, it's not possible to remember everything and consult every time this specification to check, did you call this correctly? For example, look at this. If format was component less than 64 bits, that's crazy. And of course, this can be automated, and this is done by so-called layers. There is a special software, special code, which checks for correctness. It basically checks all these rules, would keep all the state, and do a lot of checks. Because of this, layers are kind of debug thing, which you must use during development, but you turn it off during the actual running of your program. Because of course you don't want to spend time and you want your application to be very performant. So yeah, that's about layers. And there are multiple ways to turn these layers on. One of the ways is, as you can see, to provide the layers here during instance create info. Another way is to use environment variables, but I prefer to use a special tool from Kronos, I think it's from Kronos, called vk-config, the GUI version. And here we can just turn to use layers for any Vulkan executable. I don't know why it prints me this weird checkboard pattern today. It's probably because this field. Here we select which layers we want to use, and there are multiple layers. This is validation. It checks what I showed, the correct usage of the API, and we can turn some features like shader debug printf, which we'll use. Another, for example, is API dump. When you turn this layer on, it will print all the Vulkan calls, all the functions. For example, here when we use this thing, actually we can try it. Let's turn it off for now, and we will see how this tool works. But yeah, I want to say that this tool is essential for Vulkan development, and the layers we will enable through this tool, because for me it's very convenient. So that's why we left here this field's empty, and that's extensions which we will use with this instance. Now the application info, I think it's some random stuff. It's maybe not even necessary, I don't remember, but anyway I just added it here. Again, like any info, it has some type. I will not mention this anymore in the future because they are similar. The next structure as well, I will mention this only when actually we need some chaining. So application name, I don't know honestly why like this info is necessary. This is maybe for drivers. I don't know, if you have a lot of money, you just go to NVIDIA and tell guys, here $1 billion. If you see the Vulkan application with this name, please make it super fast. And the engineers will do a special path in the driver and super optimize it. Joking, of course. And just some information. So the engine name, I don't know, Unity, Unreal, whatever. So it's not for our application, but I added this anyway. And that's how we create this thing. And now how to call it. As you see, the return type is instance or expected thing, and the previous return types all were void. Just look at the first video if you don't remember what is it. And we need to add another case for the situation then the function call is not void. Let's do it now. Yeah, it's basically the same as before. Now, instead of doing nothing, we assign the result of the expression to a variable var. And we call it like this. Now let's try to compile. Let's check the errors. It tells instance was not declared in the scope, but it was. Yeah, so the missing header. Now let's try to compile one more time. It works, and let's just try to run it. Yeah, so as you can see, it prints us create an instance and does not crash. That means that everything works as expected. And now, as promised, let's see how we can use the config tool. Let's briefly look at create instance. As you can see here, the usage is pretty simple, so not a lot of stuff. Maybe this interesting. It tells required extension names must be presented in this list. That means that if we add some garbage here, what it will print, I hope extension with this name does not exist. And let's check it. As you can see, it crashes now, but it doesn't gives us error. We don't know what's happening exactly. And the problem that this, yeah, that's interesting stuff. So in order to turn the layers on, we need to create an instance. So even if I run validation layers now, here, let's select this validation. If I run it, it will not give us any information because the instance is not created and it doesn't print. Yeah, so here we have to be careful and check the specification. Let's bring it back. I told that I will show, but of course I will not show any validation layers now because instance is not created yet. So it will not show, I think, even API dump here. Yeah, sorry guys, so before instance is created we can't do it. We have to wait until next. Yeah, but that's it with instance. So after these long hours of coding and recording the video, they finally have something simple as instance. I don't know what we achieved, probably is only 1% of what we need to achieve, but anyway, it's the first step. And the next step would be to either create a device. First, find the physical device. So on my machine I have multiple physical devices because it's a laptop with integrated and dedicated GPU. We can do this because device is as essential as instance, so any call to almost any Vulkan function requires device. But for example, to create a surface, a rendering surface, it doesn't need a device because again, surface is operating system stuff. It should work for any device the same, so all it needs is instance. And yeah, we will start next with the surface. that's it. So this tiny function actually does all the job. Again, here the GLFL library helps us a lot. As you can see, this library requires a window as input. Of course, it should be this window, but since we have a wrapper around this, I need to provide it. And yeah, I changed the graphics manager. Now it accepts the preference to Windows. The reason it's not const, and the reason why I changed here the get function from const to normal pointer is because GLFL library requires this window pointer not to be const. And in order to compile, we need to change here the main CPP and to actually pass our window here. Now it should compile. And now let's look what actually the library does, how it works. I mentioned multiple times that this window stuff is not cross-platform and depends on the operating system. Let's look here what this function does. Let's put a breakpoint. For example, here it's inside the library itself. And hit F5. We can skip multiple steps until we reach init Vulkan. And if I press F10 here, it will jump over. That's because we already initialized this library when we created a window. So we don't see what's actually happening inside. So let's go inside this function and set a breakpoint here and restart our debug session. Here we can see that this call to init Vulkan done here in our window initialization. And the interesting stuff happens, for example, here it does exactly the same as we did with extension properties. And you remember we got these properties with the help of this library, and here it iterates over names, over extensions, and just set some internal variables. So this is the first part of this operating system dependent things. Okay, so it have 24 property. We remember that we have this extension enabled, and yeah, indeed the breakpoint hits, then iterator is equal 11. So that's the first part. When we have this flag enabled, now I can continue. Now I inside in again. The second time it's already initialized, so we skip it. And here again we back to Windows Surface, and let's escape multiple times. And this is where this happens inside the create Windows Surface. If we go into this function, we see these flags, so it's enabled for XCB surface. We go inside this block, and inside we see this final Vulkan call to create this specific surface for this specific window manager for this specific operating system. So on Windows it will be another call. This file is called, as you can see, X11 window. There are many other windows, so you can see that's probably Wayland, Win32, and so on. So yeah, I wanted to say that if you do not use this helpful library, we will have to do the same. And since I do not have Windows, then I probably would not be able to show for Windows users. But here, basically, everybody can follow because this library is cross-platform. As we can see, it works. We can proceed. Nothing crashes. That's good. Let's close everything. Let's remove breakpoints. So we have the surface. And the next step would be to query the physical devices on my machine and on your machine. Get supported physical devices. So I didn't finish this function because it requires more steps, several steps. So let's start with just simple stuff. First, as before, we already saw this pattern. First, we want to get the number of physical devices on my machine. So for this, first we need to get just the count, the number of the devices. For this, we call this Vulkan function with null pointer as the last parameter, and after the number of devices, we allocate the necessary amount of memory and provide it to this function, and the function fills this memory with physical devices. And after this, I wanted to do several steps. The simple step is to print information, and for this I need to get this information, and we will do it with some wrapper around Vulkan get properties function. And in this step, I want to check that the device supports it or not. If you remember, the idea was to run mesh shaders sooner or later. And mesh shaders require special hardware, so not every device supports this. And of course, we can have multiple devices in the system, but maybe some of them, maybe all of them will not support it, or if you are lucky, then all devices will support what we need. And to check if devices support it or not, we will use another quite confusing thing in Vulkan. It's called features. So yeah, this triplet of layers, extensions, and the features, they are quite similar but very distinct things. So that would be the second step. For now, let's create a function to get the properties and just maybe to see how many devices I have and to get their names. So this function, get physical device properties, is just wrapper around this Vulkan function. That's this rare case where the function doesn't return result. So it's supposed to be always working. I wish every Vulkan function be like that, but yeah, we have what we have. Yeah, as you can see, we are using this number 2 properties. Then the first version was introduced. There was physical device properties, just one without any number. And the reason why they added, as you can see, it doesn't have this S type and it doesn't have the P next structure. So with these original properties, you can't basically chain another stuff. We do not use chaining here, but anyway, so maybe for the case we need this, I decided to use this number 2, but I think number 1 will work as well. As you remember, I'm still using the struct helper, so it returns the S type. The reason I added the wrapper is because we need to call this multiple times, and just to not copy paste 4 lines, we will just copy paste 1 line. Back to get supported physical devices. Here we call it last when we have the list of supported. We just print the names, and I just repeated this here when we want to filter basically devices. But let's just see how many devices I have on my machine. Let's compile, let's run it with debug mode. As you can see, I have 4 devices. This is a laptop with 1 integrated Intel GPU, 1 discrete. I don't know why the driver gives me the 2 GPUs with the same name. I don't know, honestly. Maybe I have messed up with driver installation and I have 2 different drivers on my system. And this is the software implementation of Vulkan. I know that when you install a Mesa open source driver, you automatically get this LLVM pipe thing. But I don't know. I never used this. So on this machine, I have this number of devices, and now we just need to run and see which device support what we need, and we need mesh shaders and plus some other stuff, you will see. here how we check if device is supported or not. So we iterate over every device, get it properties. The properties are just for printing the name of the device, and we call this check physical device support function. Right now it does two things. First, it checks the Vulkan version it supports. As you remember, we created this helper struct where we defined once what we want to have in our application, and here I reuse it. Before we used when we checked instance version. Yeah, and we just print information. So if the major version is less than the required, it's immediately an exception, and if the major version is the same as required but the minor is less, it's also considered an error, and if the major version is greater, then everything is fine. Then we want to check features, which I do not have right now, and also we want to check the extensions. As you remember, when we discussed extensions, I told there are two kinds of these extensions: instance or device. And here we call check device extensions. Here I created this helper function directly in this translation unit, and I'm just too lazy to create a file. Probably I need to just to follow the same convention, but let's think that's just to show how to use anonymous namespaces in C++. Yeah, so this little function, what it does, again, the similar pattern we saw before. First we need to get the count, then we need to call the same function second time to get the actual extension properties, and then we want to do something with them. Extensions have version, it's not interesting for us, and the name, so it's basically just a string, the name of the extension, and we need to compare it with some things we want our device to have. Since we probably will need these extensions a couple of times more, I will do similar to required instance extensions. Let's look at the helper struct. It's pretty simple. It has the print function, which just prints the names of the extensions, and it has a get function, which currently returns only one extension, which we need for our device. So as you remember, we saw this before, this extension is a device extension. We will need more, and the way we discover when we need to add a new extension here is then we hit some exceptions, or validation layer will report us that something is wrong. But for now, let's just have something. We know for sure we need a so let's add it here. Then inside this check device extension function, we iterate over all required extensions, and then we compare it with available extension. So if the required extension is in the list, of the available, we just continue our loop. If at least one required extension is not supported, we are finishing. We can't do anything with this device. And here, in this function, I just print the information, the list of required extensions. Let's try to run it to see what it will print. Let's close it and let's see what the output tells us. So it tells that it checks this first device, it's supported, the second NVIDIA device supported, then it checks the Intel integrated device. Yeah, it prints here, it's been supported, but of course it's not supported, and the reason, let's just recompile and run it once again. Intel device is not supported because I have probably the old driver, or the device itself is not that new. It may support mesh shaders, but it doesn't support this 1.3 Vulkan version, so we skip it. And then it checks this software device. On my system, it's even worse than Intel device. It's only 1.1. So in the end, I have two supported devices, which is one. I don't know again why it's two. I have one thing to check as well, the features. So first, let me write some code, and then on the code I will show what are exactly these features. Excellent. So I wrote quite a lot of code, and in the beginning it could look a little bit scary, but in reality it's pretty simple. So it's more like a C++ exercise than Vulkan. And let's walk through the code, what it does. So last time we finished inside this function, check physical device support. So we check device extensions, and the thing which remained was features. Now, what are features? As the name suggests, it's the thing which you can turn on, like different features. For example, the mesh shader, it's a feature which not every GPU supports. And in Vulkan, the features are disabled by default. And with time, as GPUs develop, the new features appear, and the vendors add different features of the GPU through extensions, for example. Or if the feature is quite common, it becomes part of the core Vulkan. Similar to what I did with a different require something, like required API, required extensions, I created a small helper called required features. Currently, it consists of multiple different helper classes which are organized in this features folder. The main one is required features, and let's look briefly what it does. Why there are many features and how to use them together. We had multiple times discussion about the pnext pointer and how we can chain different structs together, and this is example where we will use it. For example, let's just open some random stuff. I will just show the core function which is necessary to get the features. It's called vk get physical features. It has features too because it accepts physical features to structure. This structure has the pnext pointer, and these were the vanilla features in version 1.0, and it doesn't support the pnext properties. Probably people didn't expect that there will be so many different features added. So it's just the struct which lists available features at the time. That's why the physical device features 2 was introduced. They added this pnext, and the way we can query which feature supported by the device is through this function. And as you can see, it's only one function. There is no function like get physical device mesh shaders features, for example, and for any other different kind of features, and there are many different features. When you install the Vulkan SDK, it also installs Vulkan Info. The Vulkan Info is a utility which shows different information, basically the same we're acquiring here. It's as a standalone feature. You can check different devices, and here it's quite lengthy because it lists all devices on my machine. There is a way to reduce the number of devices by using this parameter. Now it should appear somewhere here. So these are information for the GPU. As you can see, it's RTX A5500, and if you type the word features, we can see different kind of features like physical device features, the version 1.0, and the zoo of different features, many features. We will not use all of the features. There may be a question, why, if you create logical device, why don't you turn everything on? And if you have some feature available in the GPU, why not just to make it available without explicitly saying enable this? The reason is certain features, they are mostly usable for debug. The one example I know is called robust buffer access. This robust thing means that the API introduces a lot of checks And if you have some out of memory read or write, the API will not crash, but tells you. I never used this, but this idea. And as you can imagine, since you're using this additional checks, it can be not free, right? So it has some cost. That's why you don't want this feature to be enabled by default. So yeah, they decided to disable all feature by default, and you need to enable this by yourself. For our application, we will use a small amount of features. These are mesh shader features, of course, and Vulkan 1.2 features, 1.3 features. I know it can be confused, but just think about this as a generation of different kind of functionality. So this main class required features has the main features, which we can query, and also some additional list of features which we can add or remove. We can possibly add different features at runtime, but I decided just to have this required feature, and inside the constructor it will create a number of features we are interested in. So for example, let's start with mesh shader features. So this is the interface, so all these features extend this base class, which is pretty simple. It has add to chain, check and print. So the add to chain is the thing I already told. Since we have only one function to query the features, just for a reminder, this is that function. But we have possibly many features, as you saw. We add different features by chaining multiple structs. The check function just checks, takes physical device and checks if it supports this set of features, and the print just prints some debug information. We'll see shortly. This is just the header, as you can see. It has the pure functions which every derived class has to implement. And yeah, I just added this concept, quite a new addition to C++. We'll use templates, and to have nice errors and to make it more readable, we will use a concept. Yeah, so mesh shader features extends this feature, implements these functions. So inside this class, we have the ultimate main features for this set, for this mesh shader features. And this is the way how I organize this. So the constructor just creates this thing and stores this. This is very essential because since we have a potentially long chain of different structs, different features, chained one to another, as we create this chain, as you remember, we are using pointers and we passed something to p next. And in order for this pointer to be valid in C++, the thing which pointers points to also have to be alive. So we need to store the original, the pointee of this p next somewhere. So that's why every kind of features, not temporary variable, it have to be stored for the lifetime of these features. So the constructor just initializes these features and just assigns some features from this set we are interested in. This mesh shader features, it has not a lot, just 5 different kind of functionalities, but we are only interested in these two, task and mesh shaders. And this is how I'm using this in C++. That can look quite confusing because this stuff and this pointer to a field, what is it? I will try to explain the reason why I need this. And the main reason basically is just to have a single place where we can list the required features. And also I want some debug information like the name of the feature. And in case if check returns false, I want to know which feature exactly is not supported. For example, I could say features task shader is equal to true, but in this case I'm losing the name because I need somewhere to get the name of this field, I need some data structure to store it. And for example, in this case, I'm creating the temporary variable. We will see exactly how this check works. And we'll have to do the same. It will have to explicitly enable these features again one more time. And as you can see, like, it's already 2 places where it should be repeated. And if you want to add someday one or remove, it will be easy forgotten. So I decided to keep the list of things we need to turn on and to check in the separate data structure. In this case, I'm using just std map, where I can use the pointer to the field and the name of this field. If you're not familiar with this concept of pointers to members, in C++, you can take a pointer to a member function, and you can take a pointer to a member of a struct, for example, like here. And this is, by the way, the signature. If you want to type the data type of the pointer to a member, these pointers, they're not normal pointers. They do not point to some place in memory. I think for functions it can be, but I think it's more than just 8-bit pointer on 60-bit machine. Pointers to member should be just the offset for this field. So for example, here this mesh shader field has offset of whatever the size of this thing, 8 bytes, this book 1 byte, so it has offset of these 3 fields, the next field offset plus this field, and so on. We will not use pointer to functions, only to members. And the way we are applying this is through this weird looking stuff. How this works. The pointer to a member, maybe it depends on implementation, but on my machine it's just offset, so you can't just use it alone because it's just offset number 4, for example, or 8. And when we apply this, we're taking the structure created somewhere in the memory, like here, and it just tells, please take some field on this offset, please take the pointer to this member and apply this to this function, and in this case it will be through this early looking syntax. In simple words, I'm just turning on these fields for this data structure and just set it to true. We will need this later, but that's just explanation because it's all the same for different kind of stuff. The add to chain member, it's just, as the name suggests, it just takes some pointer. I'm expecting this to be the pnex pointer, and it just assigns the features to this pnex pointer and returns the pnex of these features. For example, if you want to chain further to add another features, we will assign this to this variable, and so on. The print function just prints things. It uses this helper, and it just iterates over this map and just prints the first element of each pair, which is just the name. So it just print information just to quickly see what we want to enable. And the most interesting function, in my opinion, is this check function. Takes physical device which we want to check. This is how we are doing this. We have this function which returns the features for this device. We are creating the temporary. Why we are not using this, you may ask? Because here this features is what we want our devices to use, and here this features is what actually the device supports. We need to create this temporary variable. We use the pnex pointer to use this temporary field, and we provide these features to the Vulkan function. After this call, all the members of this struct and this struct will be filled with some real numbers for our device, and we iterate over these features because we are interested in these features for this class. So it iterates over mesh shader features and checks if every member taken from this is supported for this device. If we find that something is not supported, we just print it's not supported and set the flag to false, indicating that this device is not sufficient for us. That's basically it. And let's briefly now look through different features we will use. The top level required features has these top level features. It has these two things. The first one allows to render something in wireframe mode. Yeah, without enabling this feature, you can't render in wireframe mode. And wide lines allows to change the width of the wireframe, the width basically of the line. Without setting this on, you will not be able to use the special function to set width of the lines. First, it initializes its own features, then it adds the features we will use for our application. And I added some implementation, the private function, because I wanted to make this class similar to other, where I use the static members, for example, print as a static, so it creates temporary features just to print something, and the same for check. The get chain is quite special, and we will not touch it today. Later, we will see how this works. Here in implementation, it just checks every feature for features too, and then it goes into each of the added family of features and just checks individually if they are supported or not. With Vulkan 1.2 features, we will use descriptor indexing. Usually people know this by the name bindless rendering, but the API uses the name descriptor indexing. And this is the list of the things we needed. I will not explain this today. Maybe for now we can disable everything. And we will find out what we need to add later when we start to implement things. The layers should complain because, as I explained, if you use something without enabling this is not correct and it's not supposed to work. But the layers can detect this and report. The scalar block layout is used for shaders. Shaders are quite weird because they require members to have a special alignment. So by default, you can't use, for example, a vector 3 in push constants and in buffers. So because Vulkan expects vectors to be aligned by the float 2 and float 4, like the float 3 is not available. But this extension allows us to use vector 3, for example, in buffers and push constant, and it will work. Let's just keep it for now. I don't remember actually, will I use vector 3 somewhere or not? If I will use and if I will not forget, I will try to disable this and show what actually happens and why it doesn't work. But this is what we will need, and we will enable this as we go. Before Vulkan 1.3, this I think was extension, this didn't exist, or maybe also was an extension. 1.3 just standardized basically added to the core API. I can't say right now why exactly it's needed, so let's just keep only one. Dynamic rendering, this is the thing which allows us to make a code a little bit simpler. It allows us to not to use render passes in the original Vulkan 1.0. If you want to draw something, you need to create a render pass, at least one, and every render pass has to have at least one sub pass, and it's just quite a lot of code just to manage this render passes and sub passes. But with dynamic rendering, we are not required to do this, and this makes code simpler. Let's use only one for now, and we will find out whether we need, or maybe we will not need, another two. And the rest of the class for 1.3 features and 1.2 features is the same as for mesh shader features, as we saw. So how this works? We have this call, get supported physical devices. And here just prints. I wanted to use a static simple call, that's why I introduces this print, which calls the implementation on temporary object. Here temporary is fine because we don't need this object after this print exits. And then it goes into the check physical device support, and this is where we call this check function. So basically it takes the device and we call this for every device, where it calls check implementation, and this check implementation just applies these pointers. Let's see if it compiles. Let's run it with F5. And here it prints all the features we will use. Let's actually see what happens if I add a feature which is not supported on my device. As it turned out, my device is quite good and it has a very good support. A lot of different features are covered here. For example, this has everything true. And I want to check what features we will use. For example, mesh shader features. Here, every feature from this family is supported. 1.2 features. Everything is supported here as well. I don't see any faults. Maybe 1.3. So here I see the one single feature texture compression SITC. I don't know what is it, but it's not supported on my device. So if we go to this 1.3 features and add this, texture compression, what should happen? So on this check function, we will query the feature and it basically will return this struct, the same as here, with everything true except this one field. And then we go through this returned struct and check if the things we are interested in are supported. And this thing is not supported, so it should be false. And we check. If it false, that's error. And it should print us this line. So let's check this. Okay, application exits. That's a good sign. And here it tells features 2, extension, feature 1.3. So this one, which is not supported. And here we check NVIDIA device. And here it tells us that this feature is not supported, so the device is also not supported. That's the same GPU, the same story. And these two GPUs, as you remember, the version of API is not supported here, so it doesn't even check the features. So yeah, it tells us that failed to find supported devices. So I do not have any devices on my machine which covers all the requirements. So let's remove this. Compile it again. Check one more time that it works. It works. Very good. And that's it regarding the physical devices. So after this call, we have the list of supported devices. On my machine I have 2. The next step would be to create a logical device, and this is where we will need this required features again. And for now, let's just create a tab for the next function. And I think that should be enough for this video. Yeah, that's it. So I place here the to-do. Let's compile it everything one more time. That's, I think, it for this episode. The next time we will start by filling this function. I call this change physical device because since we can have multiple, it would be possible to change devices at runtime. That's not what we will use, but it's just maybe as a homework for you to implement this change. I actually enjoy that you can do this in the computer games, select different devices. I don't know why, but it just looks professional. So without restarting the game, you can change and everything reinitialized. It just looks cool. For now, let me comment everything. So this thing we do not need anymore. It was a temporary information. Let me just skim through it. It looks okay. So it was part 1. Let's think that this is completed. And you can use it if you want to follow. I hope to see you in my next episode. So yeah, take care.